This session explores practical implementations of eco-urban design across Europe, highlighting strategies that integrate sustainability into city development. The primary focus is on the Freiburg-Vauban district in Germany, a benchmark for low-energy housing, green mobility, and community-driven design. Complementary case studies, such as Hammerby Shoested, Western Harbor Malmö, GWL Terrein in Amsterdam, and Smart Licky in Zidlakovice, illustrate diverse approaches to resource efficiency, renewable energy integration, and resilient urban ecosystems. Together, these examples provide a comparative perspective on best practices and innovative solutions shaping sustainable cities. Also, all of these approaches apply ecological principles within the framework of spatial planning. The following sections summarize these principles. Ecological spatial planning frames territorial development as a balance between human demands and the natural thresholds of the landscape. By recognizing carrying capacity and resilience, planning respects the ecological and physical limits of territories, preventing irreversible degradation and supporting long-term environmental stability. These limits function as safeguards against overexploitation, ensuring that development occurs only where the landscape can sustain it. With a strong focus on climate change adaptation, spatial planning integrates nature-based solutions, green infrastructure, increased water retention, and enhanced ecological connectivity. These measures reduce vulnerability to climate-related hazards, such as droughts, floods, and heat waves, while strengthening the landscape's ability to absorb and recover from disturbances. This forms an integrated approach, in which sustainable land use operates within ecological boundaries to create resilient landscapes capable of adapting to climate change while preserving essential ecosystem services and supporting human well-being. The concept of land take refers to the permanent conversion of natural or agricultural land into built-up areas or infrastructure. In the context of sustainable spatial planning, this process cannot simply be offset by administrative measures. True compensation requires ecological restoration and actions that deliver measurable, nature-positive outcomes. Compensation should ideally occur as close as possible to the affected area to maintain ecological continuity and reduce fragmentation. Locating compensation sites within existing ecological networks or along identified landscape corridors helps preserve species movement, ecological processes, and long-term connectivity within the region. In urban environments, compensation, or also mitigation, measures can take the form of nature-based solutions that enhance biodiversity and reduce environmental impacts associated with impermeable surfaces. Examples include green roofs and living walls that support urban habitat, permeable pavements that improve water infiltration, urban wetlands for stormwater retention and habitat creation, and the restoration of brownfields into biodiverse parks or community green spaces. These interventions improve microclimates, reduce heat island effects, and strengthen ecological functions within densely populated areas. In open landscapes, compensation strategies focus on restoring ecosystem functions across larger spatial scales. This may involve rewetting degraded wetlands, introducing agroforestry systems that combine production and ecological value, establishing riparian buffer zones to improve water quality, implementing soil regeneration practices, or creating rewilding corridors that enhance species movement between isolated habitats. Such measures increase resilience to climate change while supporting agricultural productivity and landscape-scale biodiversity. The overarching framework tying these actions together is green infrastructure. By viewing compensation not as isolated projects but as interconnected elements within a multifunctional network, planners can ensure that ecological benefits accumulate at landscape scale rather than remaining fragmented. This integrated approach supports ecosystem services, enhances resilience, and contributes to long-term sustainability goals for both urban and rural environments. When discussing spatial development, it is crucial to distinguish between construction on previously undeveloped land, so-called greenfields, and the redevelopment of brownfields. Greenfield development often appears attractive due to the availability of open land and fewer immediate constraints. However, it carries significant long-term costs: irreversible soil sealing, fragmentation of ecosystems, loss of agricultural potential, and increased infrastructure demands. Brownfield redevelopment, by contrast, represents a sustainable alternative. These sites, abandoned industrial zones, derelict commercial areas, or underutilized urban plots, already possess infrastructure connections and are embedded within existing urban fabric. Their reuse reduces pressure on natural landscapes, revitalizes degraded districts, and supports compact city models. Moreover, brownfield regeneration often stimulates local economies, creates jobs, and enhances social cohesion by transforming neglected areas into vibrant spaces. From a policy perspective, the European Union has set a clear direction through the No Net Land Take by 2050 strategy. This initiative emphasizes halting the expansion of built-up areas into natural or agricultural land, aiming instead to recycle and optimize existing urban land. The strategy aligns with broader EU goals on climate adaptation, biodiversity protection, and the circular economy. For planners and policymakers, this means that brownfield redevelopment should be prioritized as the default option. Greenfield projects should be considered only when no viable brownfield alternatives exist, and even then, strict ecological safeguards must be applied. The preference for brownfields is not merely an environmental stance, it is a rational economic and social choice that ensures long-term resilience, reduces land consumption, and supports sustainable urban growth. The following slides will present examples of best practices, dominated by the example of the Vauban district in Germany, which served as an inspiration for other cities. The Vauban district, located in Freiburg, Germany, represents a pioneering example of large-scale sustainable urban redevelopment. Its transformation from a former military base into a vibrant residential neighborhood demonstrates how brownfield sites can be repurposed to support contemporary ecological and social objectives. The planning strategy prioritized compact urban form, mixed-use development, and a strong connection to the surrounding natural landscape, ensuring minimal ecological footprint despite relatively high residential density. Vauban's design framework intentionally integrates ecological principles across transportation systems, housing topologies, and public green spaces, creating a coherent model of urban sustainability. By embedding energy-efficient architecture, car-restrictive mobility planning, and multifunctional green infrastructure into the district's core design, Vauban illustrates how ecological integration can serve as the foundation for resilient, low-carbon urban living. Vauban's spatial and infrastructural design showcases a comprehensive application of ecological urbanism, with mobility, energy, and landscape systems all optimized to reduce environmental impact. The district's car-free zones and extensive cycling infrastructure fundamentally reshape mobility patterns, positioning active transport as the default and significantly lowering transport-related emissions. This mobility framework is complemented by a building stock dominated by energy-efficient topologies, including numerous passive houses that minimize heating demand through advanced insulation, airtight construction, and passive solar design. At the landscape scale, community green spaces and interconnected ecological corridors enhance local biodiversity, support microclimate regulation, and provide accessible recreational environments for residents. These vegetated systems work in concert with decentralized solar energy installations and localized water management measures, such as pervious surfaces, swales, and retention basins, to create a resilient urban ecosystem. The Vauban district in Freiburg, Germany, represents one of Europe's most advanced real-world applications of eco-urban design, demonstrating how a former military installation can be systematically transformed into a model of sustainable urban living. Conceived in the 1990s and developed through strong cooperation between the municipality, citizen groups, and environmental organizations, Vauban illustrates how ecological principles can shape mobility systems, energy performance, social governance, and landscape structures in a holistic and integrated manner. The following principles form the basis of a functional system and are transferable to other locations: land use transformation and ecological urban form. The conversion of a decommissioned military base into a dense, mixed-use residential neighborhood reflects the principle of land recycling, a core component of sustainable urbanism aimed at reducing greenfield expansion. Vauban's urban form emphasizes compactness, short walking distances, and functional clustering. This spatial configuration minimizes transport demand while preserving surrounding natural landscapes. The design incorporates permeable green corridors that link the neighborhood with adjacent forested areas, enhancing ecological connectivity and allowing species movement through the urban fabric. Sustainable mobility. Prioritizing low-carbon transport. Vauban is internationally recognized for its car-free planning, a hallmark of eco-urban design. Private car ownership is not prohibited but culturally and economically disincentivized. Parking is located at the periphery and requires additional purchase of parking place, while internal streets are designed as stellplatzfrei, parking-free, pedestrian priority environments. This design elevates cycling and walking as default mobility modes, supported by continuous, high-quality infrastructure. Such mobility planning not only reduces emissions but also shapes a quieter, safer, and more socially interactive public realm. The mobility hierarchy implemented in Vauban, pedestrians first, cyclists second, public transport third, and cars last, demonstrates a fully realized application of sustainable transportation theory. High-performance building topologies and energy systems. A defining characteristic of Vauban's housing stock is the widespread use of passive house standards, emphasizing ultra-low energy demand through optimized insulation, airtight construction, heat recovery ventilation, and passive solar gain. Many buildings exceed national efficiency requirements, showcasing a scalable model for energy-positive neighborhoods. Complementing these buildings is a decentralized network of renewable energy systems, including rooftop photovoltaic arrays and solar thermal collectors. Combined heat and power plants running on wood chips and biogas further anchor the district's transition toward local, carbon-neutral energy. These systems demonstrate the principle of distributed and resilient energy infrastructure, reducing reliance on centralized fossil fuel grids. Integrated green infrastructure and water management. Vauban's landscape strategy supports ecological performance at multiple scales. Community gardens, parks, and linear green corridors provide both recreational space and habitat value, contributing to elevated biodiversity within the urban environment. The neighborhood integrates sustainable urban drainage systems, such as swales, infiltration basins, and permeable surfaces, which manage stormwater on site and reduce pressure on municipal drainage systems. This application of eco-hydrological design mitigates flood risk, enhances groundwater recharge, and introduces microclimatic cooling benefits. Social sustainability and participatory governance. A distinctive aspect of Vauban is its strong culture of civic participation. Residents played a substantial role in planning through cooperative housing developments, neighborhood assemblies, and citizen-led initiatives, e.g., the Forum Vauban. This participatory governance embodies the eco-urban design principle that sustainability requires not only technological solutions but also social empowerment and community stewardship. The resulting neighborhood culture fosters high levels of environmental awareness, collective responsibility, and place-based identity. Vauban stands as a benchmark in eco-urban design because it demonstrates not merely isolated examples of sustainability, but an interconnected, systemic implementation of ecological principles across transportation, energy, landscape, water, and community governance. Its success derives from the synthesis of technical innovation, participatory planning, and a spatial structure that facilitates low-impact living. As such, Vauban serves as both a practical precedent and an inspirational template for future sustainable urban districts worldwide. The long-term outcomes observed in Vauban demonstrate the effectiveness of its ecologically oriented planning strategies. The introduction of green corridors, community gardens, and diverse vegetation structures has significantly increased local biodiversity and overall green cover, reinforcing the district's ecological resilience and enhancing habitat quality within an urban context. These environmental gains are closely tied to Vauban's exceptionally low per capita carbon footprint, achieved through the combined impacts of car-restrictive mobility planning, energy-efficient building standards, and widespread adoption of renewable energy systems. Vauban's success has positioned it as an influential model for sustainable neighborhood development, inspiring similar initiatives and policy adoption in cities across Europe seeking to replicate its integrated, community-driven approach to ecological urbanism. Hammarby-Sjöstad represents one of the most comprehensive examples of system-level eco-urban design in Europe. The transformation of a contaminated industrial shoreline into a dense, mixed-use neighborhood provided an opportunity to implement the innovative Hammarby model, an urban metabolism framework linking energy, water, and waste flows into semi-closed cycles. Waste heat is captured for district heating, biogas from organic waste fuels buses, and stormwater is treated through natural filtration ponds before re-entering the aquatic ecosystem. Mobility planning prioritizes public transport and active modes, reducing private car dependency even in a relatively dispersed urban setting. Residential buildings meet high energy performance standards and are supported by smart metering and renewable energy technologies. The district's blue-green infrastructure enhances ecological performance by improving water quality, supporting biodiversity, and mitigating urban heat island effects. Hammarby-Sjöstad is widely regarded as a benchmark for integrated sustainability in urban redevelopment. Western Harbour developed for the 2001 European Housing Expo, showcases ambitious sustainable urban design guided by a commitment to full renewable energy supply. Energy is generated through a combination of offshore wind power, extensive photovoltaic installations, and geothermal heat pumps, establishing the district as one of Europe's earliest attempts at climate-neutral urban living. The urban form emphasizes compactness, permeability, and diversity, with a rich network of pedestrian passages and cycling routes that encourage active mobility while significantly limiting car use. Landscape design plays a central ecological role. Green roofs and green belts extending from the coastline enhance biodiversity, regulate microclimates, and create attractive public realms. Water features and stormwater channels function as both aesthetic elements and components of sustainable drainage systems. GWL Terrain is one of Europe's earliest car-free ecological neighborhoods, implemented during the 1990s on the site of a former waterworks facility. The decision to prohibit private car ownership within the district fundamentally shaped its design, yielding a compact layout with generous pedestrian and cycling spaces and a calm, socially oriented streetscape. The architectural approach emphasizes energy efficiency, sustainable construction materials, and a scale that supports strong community identity. Green courtyards, communal gardens, and carefully managed open spaces enhance biodiversity and promote informal social interaction. Governance in GWL Terrain is notably participatory. Residents remain heavily involved in local decision-making, maintenance of shared spaces, and the enforcement of car-free principles. The district has served as a reference for numerous European cities seeking to replicate low-car or car-free urban models, demonstrating the viability and long-term social benefits of mobility-focused ecological planning. Smart Liky represents the first comprehensive attempt in the Czech Republic to develop a fully smart and sustainable urban district, conceived as a demonstrative model for environmentally responsible and technologically advanced urban development. The concept integrates ecological design principles with digital innovation, aiming to create a neighborhood that is not only low impact but also adaptable, efficient, and socially inclusive. A central ambition of the project is the carbon-neutral operation of all buildings, achieved through a combination of high energy efficiency standards, renewable energy production, and intelligent building management systems. Smart technologies, such as real-time energy monitoring, adaptive lighting, and automated control systems, enable continuous optimization of resource use while supporting user comfort and lowering operational emissions. Water sustainability is addressed through greywater recycling, rainwater harvesting, and smart irrigation, significantly reducing potable water consumption and enhancing resilience to drought conditions. The district's blue-green infrastructure also contributes to microclimate regulation and urban biodiversity. Crucially, Smart Liky places strong emphasis on social cohesion and community life, integrating public spaces, shared facilities, and participatory governance models to build a vibrant, inclusive environment. This social dimension elevates the project beyond a purely technological showcase, positioning it as a holistic example of eco-urban development where environmental performance, innovation, and human well-being are closely interconnected. Smart Liky incorporates a comprehensive set of design and technological strategies that position it at the forefront of sustainable urban development in Central and Eastern Europe. The district's building stock is based on passive and energy-efficient construction principles, significantly reducing operational energy demand. These buildings are complemented by extensive photovoltaic installations placed on rooftops and parking structures, enabling local renewable energy generation and contributing to the project's carbon-neutral ambitions. A distinctive feature of the district's infrastructure is the integration of biodynamic public lighting and smart grids, which optimize energy use through adaptive technologies that respond to real-time conditions and user activity. This modern energy system is embedded within a wider network of green and blue infrastructure, including parks, community gardens, rainwater retention zones, and nature-based drainage solutions. These elements work together to enhance urban biodiversity, manage stormwater sustainably, and improve microclimatic comfort. Mobility planning in Smart Liky further reinforces its ecological mission. Shared mobility systems, such as bike sharing and reduced on-site car parking, intentionally shift transportation patterns away from private car dependence and towards more sustainable, low-emission modes. The district also places strong emphasis on social innovation. Community hubs, co-working spaces, and shared workshops promote collaboration, local entrepreneurship, and social interaction. Importantly, the development process includes participatory planning, giving residents a meaningful voice in shaping their environment and fostering long-term stewardship. These examples demonstrate that ecological planning principles can be effectively applied at the neighborhood scale, where integrated spatial, environmental, and social strategies reinforce one another. The Freiburg-Vauban district serves as a particularly influential and replicable model, illustrating how sustainable mobility, energy-efficient buildings, and green infrastructure can be combined into a coherent urban system. Such holistic, cross-disciplinary design not only reduces environmental impacts but also enhances everyday quality of life, strengthening community well-being and resilience. Integrating ecological principles into spatial planning and urban design is fundamental for achieving long-term sustainability and resilience. Ecological planning moves beyond traditional land use strategies by embedding natural processes into decision-making frameworks. This involves safeguarding ecosystem services, such as water purification, carbon sequestration, and biodiversity maintenance, while ensuring that development respects environmental thresholds and carrying capacity. These principles prevent ecological degradation and reduce vulnerability to climate-related risks. Interdisciplinary collaboration is essential because urban environments function as complex socio-ecological systems. Effective eco-urban design requires the combined expertise of ecologists, engineers, architects, planners, and social scientists. Each discipline contributes unique insights. Ecologists provide data on habitat connectivity and ecosystem resilience. Engineers translate these insights into technical solutions. Architects and planners integrate them into spatial layouts, and social scientists ensure equity and community engagement. The integration of advanced tools like GIS, remote sensing, and digital twins enables evidence-based planning, allowing cities to simulate climate impacts and test adaptation strategies before implementation. These technologies, combined with participatory design methods, ensure that ecological interventions are socially inclusive and context-sensitive. Ultimately, these approaches create multifunctional landscapes that balance environmental integrity, social well-being, and economic viability. They represent a paradigm shift from reactive, engineering-centric solutions to proactive, adaptive strategies that harmonize urban development with natural systems, an imperative in the face of accelerating climate change and urbanization.